Yeah, but whatever changes I'm making, it is not happening live, right? Yeah, yeah, yeah. Yeah, yeah, sure. Good evening. So as we discussed last time, today is going to be a Q&A from you on topics up to week 5. Uh, Content for week 6, we will be discussing. So week 6, assignment submission is happening on Wednesday, which is 28th October. So our contact hour will be on all Tuesdays. So next contact hour, uh, weekly contact hour is going to be on Tuesday, 27th October at 5 p.m. And this particular contact hour will particularly discuss week 6. Now, week 6, you actually had concepts of mode field diameter, dispersion, uh, and PMD. These are the contents for week 6. This we will be discussing on Tuesday at 5 p.m. next Tuesday at 5 p.m. so that you have sufficient time to go through all the sessions, and uh, that way we will make it more effective, like what we discussed last time. But today I'm here to discuss any issues you have had for content up to week 5, including the MATLAB code or including the model solutions or any of the content. So please type your questions and I will try to answer that. So you need to type your questions. I don't see any questions yet. So I'll pick up a question that was asked in the forum, uh, course forum, and try to answer that. One of the questions which was asked in the forum was about bending laws. And the question was this what is happening in this particular video at this particular time, but what is the use of bending laws and how is it calculated? So the forum question was, what is the use of bending laws? Well, typically in communication systems, we don't need bending laws, so there is no use for bending laws, first of all. Okay, uh, but bending laws is something that is something unavoidable, because when you lay fibers, especially you have seen fiber to the core, fiber to the home, uh, you are bending the fibers at corners and room corners and so on. Right? So all the theory that we derived, if you remember, we solved Maxwell's equations for the fiber, assuming that there is no change along the length of the fiber. It is all longitudinal. Longitudinally, there is no variation, right? Which means if the fiber had a refractive index profile like this, which is as a function of radius, this is refractive index. Uh, that refractive index profile remains the same irrespective of which distance, or at whatever distance we are considering. So in that sense, we made an approximation there. But that approximation is true so long as the fiber is not bent very sharp. Now let's see what happens when you bend a fiber. So you see, when you bend a fiber, I'm just drawing an exaggerated picture. When you bend a fiber, this is what happens. So this is the cladding, right? So your if the fiber was so let me just draw an exaggerated picture where the fiber was actually straight, and then it started bending like this, right? So in this region, of course here it was all straight. So in this region, for instance, if the refractive index profile was this, in this region here, for instance, if I have to change my axis of reference to my orthogonal axis has the transverse axis has shifted. So my refractive index profile is still the same, but what happens is, if you look at this bend, uh, let's say you can talk in terms of total internal reflection. You had total internal reflection corresponding to this angle where theta I is greater than theta c. But now if the light is bouncing, and let's say it reaches for example bent region where my normal is somewhat like this, and if the light is coming in at uh, depending on the direction of the bend, if the light is coming in at theta I prime, which is less than theta c, what will happen is, instead of getting reflected, it will get refracted. So bending can cause this phenomena. It may result in loss of energy. Now, how do you deal with it in the wave picture? For the ray picture, it was like this. It was fine. We can always imagine that the angle of incidence, if it becomes less than the critical angle, then you have transmission, and transmission into the cladding is not something that we want. Uh, but how do you explain this in the wave picture? In the wave picture, the way it is explained is that uh, you say that up to this length, the refractive index profile looks the same, right? After in the region where it is bent, the transverse axis has rotated. So you do something called as conformal mapping, which means that had the transverse axis remained the same as what you had earlier, you can imagine that the same effect of bending can be produced by changing the refractive index profile such that in the bent frame of reference, the refractive index looks like this. So let me explain this. So what you do is in this bent region, you just imagine that the refractive index profile now has become, for instance, like this, right? You transform the refractive index profile, which will, through this process called as conformal mapping, and now you solve your wave equation for this refractive index profile. So it's not very easily solvable because you cannot write two differential equations, one for core and one for cladding separately, because the equation for core, you can still write it, but then the equation for core will have, you cannot write n1, it'll be n1 as a function of radius. So it becomes a little more complicated to solve, but it is still possible. uh, uh, you can solve that. So that's how people do that in the wave picture, and this is usually done through numerical simulations. Okay, so so the question is, coming back to the question, there is no particular use of bending loss in a communication system, but of course in optical sensors what people have done is they have made, for instance, even in IIT Madras, there is a group which does what is called as this is called as a U-bent sensor. So which means that you make the core, this is the core that I have drawn, you make the core, you bend it as a U. So clearly you are allowing the light to escape into the cladding, because at some point it will not satisfy the condition for total internal reflection. And whatever survives comes through the output, right? But some amount of energy is clearly lost. But you know that the amount of light that gets transferred to the cladding is now dependent on the refractive index of the cladding also, because that decides how far away are you from total internal reflection. So what you can do is you can put analytes, you can put sensing materials which or rather, if you have materials which absorb this light, or rather if you send that wavelength of light for which this material absorbs, it means that the light that is getting leaked out will not get returned back. Or in other words, what I can say is that the total internal reflection now gets controlled by the concentration of the material that you have in the U-bent region. So this can act as a very precise sensor, and this is used for sensing the concentration of DNA, or sensing to micromolar kind of concentrations. So that's where you would use a bend system. But typically in communication systems, you really don't make use of the bending loss. In communication systems, what happens is you're looking at situations like this, but the optical fiber itself is cabled with a metal jacket, and it is so brittle or rugged from outside that it's first of all very hard to bend the fiber. The cable is so made so brittle that it's not possible to bend it. But then in fiber to the home application that we have that I just talked about, it is like a yellow patch cable that comes in, that can be bent easily. But what happens if you make 90-degree bend on that? So what people have found is this empirical relation, that when you do this macro bending, the macro bending means the bending that actually happens outside, so I mean external. In case of macro bending, people have found that the loss is loss is proportional to exponential minus r over rc, where rc is something like a critical radius. So if you try to plot this, it's something like this. So as you, this is bending loss. So as you keep, so what is this R? R is the radius of curvature of this bend. So how do I visualize this R? So if I bend the fiber like this, what is the radius of curvature of this bend? So this is a large R, whereas this is a small r, because this is a part of this circle, whereas this could be a part of this circle. So this is a maybe r1, and this is maybe r2, which is somewhat here, and r1 is, let's say, here. So all what we are saying is when you bend it tighter, the loss is going to be higher, right? And this is a empirical relation, and you can write this RC in terms of A divided by this. So this proportionality constant is what comes out as empirical, but this RC is clearly n1 square minus n2 square, right? So this is about 0.2 to 0.4 micron for fibers, for the standard communication grade fibers. So this is what we had estimated. I mean, we did not derive this. It's possible to derive this, but we did not really do this. But of course, this proportionality constant would actually depend on the type of cabling and so on. Right? So that was about the bending loss. Now I have a question: is V number and V normalized frequency is the same? So V number is this usually referred to as normalized frequency also. So because you have V is 2 pi divided by lambda times Na, right? P pi A by lambda times numerical aperture. So there is an inverse lambda here. So we also refer to that as a normalized V number, or normalized V normalized. Well, I don't see a usage of the term V normalized frequency. It's called a normalized parameter. V parameter is what it is called. So another question: in week 6 assignment, there are questions on WDM, but there is no lecture of WDM on week 6 content. Let me check that. You're saying that week 6 has okay, let me see which assignment question has WDM content. Let me just open the assignment. So the first question is on material dispersion. Huh. So the question is not really on WDM. I have already defined what dense wavelength division multiplexing system is, right? We will talk about WDM like this only, right? So what is a WDM? You have multiple carriers in a certain wavelength band, which is C band, which is 1530 to 1560 nanometer. It's actually not exactly 30 to 60, something like 1528 to 1563 or something, right? So that exact number is decided by the International Telecommunication Union. And you have several carriers in that wavelength range, and each of these carriers can be now modulated and transmitted in the same fiber. That is the WDM system. Now, the question is not really testing your understanding of the WDM system, but it is trying to test your understanding of dispersion for a WDM system, right? So this is the introduction I've already given you. It has a channel spacing of 100 gigahertz, which means that the separation between the two wavelength channels is 100 gigahertz. Find the number of channels that can be used in this 1530. So I've asked you 1530 to 1560 nanometer band. In that band, how many channels can be used is the question. If we number the band sequentially from the lowest wavelength to the highest possible wavelength, what is the wavelength spacing between? So I'm saying that in the lambda axis, right? this is the frequency axis. In the lambda axis, if I call this first one as 1530 nanometer, uh, and the second one as 1530 plus whatever is this 10 100 gigahertz converted to delta lambda gives you, and you know how to convert delta lambda to delta nu, right? So you just start with c is equal to nu lambda, and then you say nu is equal to c over lambda. So delta nu is modulus of that is c by lambda square delta lambda, right? So you can convert this. So the question is, if I find the wavelength separation between the first two channels, and if I find the wavelength separation between, so let's say up to this we have 1560 nanometer, right? The last two channels, what is the wavelength separation? Uh, so that is slightly interesting, because the point we are trying to say there is that, to bring to your attention, is that when we try to do this c is equal to nu lambda, it's the product nu lambda that remains constant. So depending on what your lambda is, your delta lambda may not be the same even if your delta nu is the same. For example, if I take delta nu is equal to 100 gigahertz and calculate what is delta lambda for lambda is equal to 1530 and lambda is equal to 1560, the answer is going to be different. So this is to drive home the point that the reference in a wavelength division multiplexing system is always frequency and not wavelength. If you had used wavelength as the reference and said that you had equally spaced wavelengths, then the problem is that wavelength is a quantity that depends on the medium, whereas frequency is a universally constant quantity. So that's the reason frequency becomes the reference. So I think with this understanding, you will be able to solve those problems. The highlight of this question is that also, there are this question 8, which is saying that there is a dispersion, and so you want to find out what is the phase difference between the first channel and the last channel, uh, uh, in case of a WDM system, right? There is a question which says, given D is something, find the phase mismatch of the generation of higher frequency content for a WDM channel spacing of 50 or 100 gigahertz. Let's see if you have any other question. There's a next question which says, splitter and combiner for optical signal is in our session. Yes, we do talk about optical components, how they work. Sometime, I think in week 8 or week 9, it will appear. How do we reduce intersimple interference? That is also coming in the compensation of dispersion. So we just, in this week, we are talking only about dispersion, but the uh, consequence of dispersion we are talking about. We are not talking about compensation yet. So that will come. So compensation of dispersion is a separate topic that is going to get considered in another week. To give you an answer, what we could do is either use a dispersion compensating fiber, but these days in coherent communication systems, people do not use dispersion compensating fibers. Rather, they use signal processing to compensate for the dispersion. Uh, have any other question? Please type in. Let me see if there is any question in the forum which is not answered. is happening in the video at 2:15. Assignment 6 question options, both A and B are same and C and D are same. I'll check that. But let's check the options in the assignments. I do see the options are not the same, so I wonder which questions are the options same. I do see that all the options are different. So I have another question here live. What are the specifications of commercial optical fiber which is used for commercial communication? So what is done is this specifications are actually decided by um, uh, the ITU. So what you have, which is running as standard single mode fiber, uh, the standards body will, which is the International Telecommunication Union, that will decide the characteristics of the single mode fiber. So for example, what we currently use is something called as G652 standards of ITU. So let's say I want to start fabricating a new type of fabricating a fiber. If my fiber has to be acceptable for deployment, I have to make sure that this fiber satisfies all the requirements that are mentioned in this standard. Now, the standard is not just for the fiber, it is there for the cable also. So, after cabling, what are the standards? That's also there. Now, this G652 is something that is very broad. Now, under that, you have G652.1, G652.2, and so on, right? So, if you look at this standards document, G652, it will specifically say that the attenuation coefficient should be this number for 1310 nanometer. Uh, at a wavelength of 1310 nanometer, the nominal values of mode field diameter must be some value between x and y, right? With a tolerance of this much micron. It will say cladding diameter should be nominally this one with a tolerance of a certain plus minus. Then, so typically what the standard specifies are one mode field diameter, at, that mode field diameter is a function of wavelength. So this will specify at 1310 nanometer and at 1550 nanometer, right? Then you will have core, in fact, not the core diameter, you will typically have clad diameter. Okay. Then you will have core eccentricity error, which means that you would like the core to be circular, but when you draw huge lengths of fiber, it will turn out that there could be some amount of non-circularity that will come in. That is your core eccentricity error, or maybe this is also called as concentricity error. Maybe not eccentricity because it's not elliptical. It's concentricity error. It will say that okay, it will be it should be concentric within 0.6 micron, 0.5 micron, and so on. It will obviously say what is the cutoff wavelength, and typically the cutoff wavelength of G652 if I remember correctly, it is 1260 nanometer, which means any wavelength larger than 1260 nanometers is a useful number to remember. Any wavelength larger than 1260 nanometer is going to work as a single mode fiber. Then it will also tell you the specifications on macro bending loss. So for instance, they will say that the macro bending loss must be maximum of something like zero point 0.1 dB. They'll also tell you how to measure this macro bending loss. They will say that you should keep a bending radius of something, I don't remember the exact numbers, but something like radius of 3 centimeter, which is typically 1 inch, slightly more than 1 inch, right? Because less than 1 inch, it will have a large bending loss, roughly 3 centimeter, and they will say number of turns. So I think it is typically a few hundred turns, right? 100 tons. So they will say that if I manufacture the fiber and bend it with a bending radius of 3 centimeter, and I do so, I take a post of something of 6 centimeter diameter, and I wind this fiber around. Now this is specified for fiber, bare fiber is also specified for cable. So when you bend it around, the loss should be less than 0.1 dB or something like that, right? Then they will also have chromatic dispersion parameters, right? CD parameters, which will have zero dispersion wavelength. Then you will have dispersion slope. So this will be S. We have learned it about S in the class. Then it will also have parameters on PMD. So typically it will say that the zero dispersion wavelength should be around 1300 nanometer. The maximum value of zero dispersion wavelength, so they will say that it should be between this lambda naught, should be between this number to this number. This is very important because I think this number is from 1310 to 1330 or something. I mean, again, you can check in the data sheet, or rather this is a standard document which is publicly available. It's important to know this number because in short distance communications, we know that the loss is low at 1550, but the dispersion is also high at 1550. So what we will do is, when you try to decide what is the wavelength that you should use for your communication system, you will pay attention to this dispersion value. And if it is zero dispersion in this wavelength range, 1310 to 1330, it makes sense for me to use actually the 1300 nanometer, 1310 nanometer for communication rather than 1550 nanometer, right? Because it's short distance, so I'm ready to take the loss in the fiber. Let's say my distance is only 100 kilometer, and my loss is, let's say, instead of 0.17 dB per kilometer for 1550 nanometer, let's say it's 0.25 or 0.3 dB in 1300. Because the distance is not much, I am okay with that kind of loss, but I don't have to worry about this whole idea of dispersion. So I would actually pick this wavelength, and hence this number is important. All these data center interconnects, your access networks, they all work at 1550, they all work at 1310 nanometer for this reason, because you don't have to worry about dispersion, especially when you go to very high bit rates. The bit slot becomes smaller and smaller, and the effect of dispersion, the ISI, becomes larger and larger, and so you don't want to uh, spend a lot of infrastructure on dispersion compensation. The other thing, of course, the standard document will mention is about, since we are talking about loss, that reminds me that it'll the standards law will say that attenuation. It will say that attenuation for 1310 nanometer, because that's most commonly used in the C band, 1550 nanometer, sorry, and this is nanometer. And most recently, people are trying to, this is very, very recent phenomena, people are trying to push the wavelength to 1620 or 1625 nanometer also. This is coming in what is called as the L band. It is more lossy in the L band. So the attenuation for each of these wavelengths have to be specified. They would say maximum value of attenuation should be this. at each of these wavelengths. And these standards also are very smart in the sense that they will say how the attenuation should be measured. Because how do you now measure it? I mean, what kind of sensitivity you should have in a power meter to measure that attenuation and so on. Same with dispersion also. They will also say that the standard documents will also say that you have to measure the dispersion using this method. There are multiple methods to measure dispersion in a lab, but they would say that, for example, interferometric method is one of the methods. So we'll say that MPI, that is interference between the modes, that will tell you the dispersion, right? I mean, we are not going into the methods, but they would actually say what method should you use to measure the dispersion, and then you have to comply with the standard. So they do this, and then again there are. So as I said, there are these G652 is one basic class of documents. Then you would have G652.A, point B, G652C, D, and so on. Each one will have some slightly different specifications. For example, there is a specification, I don't remember the exact alphabet associated with it. There's something called as bend insensitive fiber, which means if I, since we are talking about bending, we'll talk about that again. If I have a fiber, and now let's say I know that my fiber is to be laid in the fiber to the home scenario, and I want to ensure that the loss, if I do even a 90-degree bend, is negligibly small, I can make some small changes in the fiber design to achieve that. So what is usually done is the fiber core is made slightly, the diameter is made slightly larger, so the fiber is made slightly multimoded, so that at the when you bend the fiber, you know that the higher order modes, which are weakly guided, they are the ones which leak out, whereas the fundamental mode continues to propagate through the core. So that's a design for bend insensitive fibers. And so there is a ITU document which specifies what it is. As I said, it will all appear as variations of G652. So G652 point A, B, C, D, etc. Right? Each one will have a slightly different specification on some of these parameters. For example, it could be a slight difference in specification for cutoff wavelength. It could be for bending loss and so on. Right? And when you are actually trying to deploy a fiber, you have to pick the right standard that you want. For example, if it is for the fiber to the home, obviously you will pick a standard for which the bending loss is really low. So you will look in the market, which is that company which is giving me fiber that is complying to this standard. So earlier, Corning used to dominate the whole fiber drawing business. So they used to call the fiber standard as SMF 28, right? I really don't know what this 28 stands for, but it used to be. So some 20-30 years ago, 20 years ago definitely, this you would say standard single mode fiber is SMF 28, but that has become completely obsolete because there are many players, there are many fiber manufacturers around today, and ITU decided that it should not comply to one company. So the International Telecommunication Union will have a specific, what do I say, a consortium which will have telecom operators, telecom users, telecom companies, etc., fiber manufacturers, who will sit together and say that, okay, this is what the performance that we want, and then the different companies, fiber manufacturers, will go and figure out how to achieve that performance, right? So that is the introduction to the standards. Let's see if there are other questions here. Explain the concept of Lambertian pattern, which was asked as a last question in assignment 2. Solution is given, but concept is what I want to understand. Sure, Vaidya, I will explain that in a bit. Why not use fiber with cutoff near 1400 long haul, so that 1550 will be more inside the fiber than 1250 cutoff fiber? That's a very interesting question posed by Michael Jordan. You definitely, it may be, it makes more sense to have more confinement with 14, 1400 cutoff. But typically, the fiber manufacturing process is a extremely expensive process. It's a very capital intensive, exercise. Um, these days, I've started hearing that. So that. How is a fiber manufactured? This is something that I explained in one of the earlier interaction sessions. So you use a chemical process to deposit the preform. Preform is something that looks like of this shape. uh, this is a magnified version of the fiber. So all the refractive index profile in the cross section that you want, you would get it in the preform first. And how do you make a preform? You will do a chemical vapor deposition process. That it's a very expensive process, extremely to be done in a controlled environment. A lot of chemical engineering goes in that. And once you make that preform, this preform is put on a draw tower, which could be like several meters high, and then it is extruded. Now, if you are talking about change in design, it means that the preform has to be changed. And it is not a good idea for people to keep changing the preforms once you get it in the production environment, because some of these processes are to be done on a non-stop basis, 24 hours, 365 days, to keep it running. Simply because if you stop the process and restart again, it's a vapor deposition process, right? So if you restart again, there could be contamination. You may waste some amount of preforms, or some amount of processed material and so on. So people typically try to keep it as one standard, because if I keep it as one cutoff wavelength, which can be used for both 1310 and 1550 nanometer. People don't like, at least the industry does not like specialty products, simply because if you, the moment you make a specialty product, the volumes come down and the cost goes up. So the best way to keep it cheap is to get a product which is usable in multiple different scenarios, so that you get a lot of value for your money and you can basically bring the costs down. So the reason why different cutoff wavelengths are not commonly available is simply because now the fiber deployment, the people who install the fiber and deploy the fiber, and actually, sorry, not even deploying the fiber, I mean deployment, it doesn't matter. The network operators will now have a freedom to either use it at 1310 or at 1550. But the moment you say that cutoff is this much, then you are constrained to use only specific wavelengths, and that's something that people do not like, right? So that's the reason. There will be a slight difference in the light speed in cladding and core. Will it have a problem? So we talked about waveguide dispersion, and the reason why we explained waveguide dispersion was intuitively through that. So if you think about light propagation through core and cladding independently, I think about light going through this core, and I think about light going through this cladding independently. Of course, there is a speed difference, but light does not get propagated that way, right? It gets propagated as a mode, as a transverse profile, right? Now, this transverse profile, the way we constructed this transverse profile is by assuming that uh, the light is propagating with different speeds in the core and the cladding. So this solution already takes care of the fact that the propagation speed is different in core and cladding. So I don't have to worry about it. Okay. Okay, let's get back to Vaidya's question. So let me just, you are referring to a specific assignment, which is last question in assignment 2. So let's get that. Assignment 2. Okay. Let me try this. So it says that the emission pattern of LED is assumed to be Lambertian. Now, Lambertian is not specific to LEDs. It is a general terminology used in light illumination science. The emitted intensity at an angle theta measured with respect to the normal that is perpendicular to the surface of the source is represented by something, which is represented by I is equal to I naught cos theta. So let's say that we have a source just like this, and if I draw a perpendicular in the source, um, the intensity at an angle measured from this, so at this angle theta is I naught, I is equal to I naught cos theta. So obviously this function becomes maximum when theta equal to 0, which means at theta equal to 0 angle I have the maximum intensity. So remember, in the horizontal axis I am plotting the intensity, not distance. Okay, so this is largest intensity that I'm seeing, and it's like, so the emission is like, so I'm trying to draw it. So at this angle, let's say the intensity is I. Look, I can make this measurement at any distance I want. Okay, but at a given distance, at this angle theta equal to 0 with respect to the LED, I have measured an I naught. I know that cos function goes to half when theta equal to 60 degree, which means that if I, so this is theta is equal to 45, this is theta equal to 60. At this point, okay, let me just redraw this so that I have sufficient space to show you this. So again, let's draw our LED structure, and this is my horizontal. Okay, and at an angle theta, so I can have the LED here, for instance, and I'm sitting here and I'm actually moving around like this, and I'm measuring the intensity as a function of angle, right? So imagine that I have something which I can rotate around, and then I'm measuring the angle, measuring the intensity at different angles. So let's say that the intensity at this point is, so this is just to show that this is the horizontal I naught. I know that at 60 degree, this I naught is half. I mean, the intensity has become half of I naught, this point. And at 90 degree, obviously there is no emission. So this is, and if I keep noting down what is the intensity at every angle, so essentially calculate cos of every angle and plot it. You can do that in a polar plot. What I'm going to get is some pattern like this. It's a very bad representation. You should actually draw this yourself in MATLAB and verify, right? So this is at 60 degree, it has become I naught by 2. This is the Lambertian pattern. This is how I understand the Lambertian pattern. Now, if light from this LED is allowed to fall on a wall at a distance 1 meter, okay? So now I am talking about distance. So let's say this distance is, so this is how the LED is emitting. Now I'm considering a distance of 1 meter from the LED. Okay, with the emitting surface kept facing the wall. the area in meter square of the wall, which the intensity is at least half the peak intensity. So this is the emission pattern of the LED, but which is the area illuminated by the wall now? So let me use another color to represent that. The light emitted in this angle, which is at 60 degree, will fall here. The light emitted in this angle at 60 degree will fall here. That's where we know that the intensity drops to, for theta equal to 0, the intensity would drop to half, not to 0. Okay, so this is where the intensity will drop to half. So in this wall, let's see if I can draw. So in this, if I draw this wall, I'll see a patch of light, right? This patch of light will have, for example, here will be my maximum intensity on that wall. At this distance, my intensity will drop to 0 because that's where this light, the angle where the intensity drops to half of this, it's not 0, it's actually half of the maximum value. So if I take a circle of radius pi r square, where r is now this distance, right? That will give me the patch which will have an intensity at least half of the peak intensity. So the problem is now how to calculate this pi r square. That's now an easy problem because I know the 1 meter is this distance. I know that this angle is 60 degree. So I can easily calculate tan 60 is my radius divided by 1 meter. So my radius is equal to 1 meter into tan 60. So the 60 degree came because the intensity dropped to half at 60. So I hope that clarifies your question. There's one more question from Michael Jordan. The main difference between LED and laser diode in terms of structure is LED has cavity, laser has cavity, and that is why laser does not have a Lambertian pattern. That is right. So the laser has a cavity, so the emission is confined. In fact, we did not talk about this in detail, but now when we did LED and laser, but now that you know the idea of transverse mode, you can calculate. I can tell you what happens in a laser cavity also. So the laser cavity has mirrors, right? And you are allowing oscillation to build only in this direction. So we talked about the longitudinal modes. We say if D is the separation between the mirrors, we said that along the length the light is confined and you have only certain modes that are allowed. But you see here in the mirrors, there is a confinement in this transverse direction also, right? So you, depending on how you're using the mirrors, of course, whenever we drew this Fabry-Perot cavity, we drew very simplistic pictures. In a free space laser, you will have something like a concave mirrors, which is a confocal cavity. You could have different types of mirrors. There are conditions for the radius of curvature of the mirror so that the cavity, there is a transverse mode formed in the cavity and so on. We did not do that in detail, but you can imagine that now there is a transverse confinement also. The light is not escaping out. So this means that the confinement not only happens in the direction of propagation, it also happens in the orthogonal direction. And whenever you have a confinement in the direction orthogonal to the direction of propagation, just like in a fiber, we will get transverse modes, which means at the output of the laser also we will get these transverse modes, right? So obviously this is not LP modes. You say that this is a TEM, transverse electromagnetic 00, or depending on what how the laser design is, you can think about. For example, in a semiconductor laser, we talked about carrier confinement, and we talked about in heterojunctions, we talked about carrier confinement. We also talked about mode confinement, right? So we said we had picked the band gaps such that in the intrinsic region the band gap is lower, so that gave us a refractive index of higher. And at that time I told you that when we do modes of the fiber, it will be clear that you will understand that mode confinement will lead to certain transverse modal structure. Of course, if you think about a structure like this, right? This is a semiconductor laser diode structure. You have this intrinsic region here, right? And you make sure that the emission, let's say, happens like this, right? So here is where the refractive index profile you should consider. So you can think about this one, which I'm drawing in pink as the higher refractive index region, and this outside as lower refractive index region. So you do have a confinement. So you have a confinement in this direction, which corresponds to so there will be this semiconductor ending somewhere, and so this corresponds to the uh, 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 longitudinal mode. So if I draw this separately, so I can show that pardon my bad drawing. Something like this. So you can imagine that there is this intrinsic region all around, right? And you can imagine that this end face has a mirror. This end face also has a mirror, right? This is the simplest way of imagining how a laser structure would look like, right? And inside this, the light is bouncing back and forth, right? And this separation is D, and so that gives rise to longitudinal modes. But if you look at light that is emitted this way, that's in this picture, you will see that in the transverse direction, which is in the direction perpendicular to the direction of propagation, in this direction also there is confinement. And we know this thickness of this intrinsic region. We know the value of N1, we know the value of N2. So this is something similar to a step index fiber, right? So we can now calculate what is the modal profile that's coming out of the system. So if I examine the light that is coming out of the system and I look at the transverse profile, that profile is going to look like this, right? It's going to be a fundamental mode. Fundamental mode, the nature ensures that the fundamental mode of any structure, whether it's a rectangular waveguide or a optical fiber, it's very hard to find a fundamental mode which is not Gaussian, right? So even for this structure, the fundamental mode turns out to be a Gaussian, right? So that's the difference between an LED and a laser. So it's not really a Lambertian. So just like numerical aperture for a fiber, you also have a numerical aperture for a laser, right? Whereas in an LED, if you take an edge emitting LED, it just emits in all possible directions. The limit is only given by the total internal reflection, right? We talked about that when we did LED. We said that the structure is like this. One section of this is this, and light is emitted actually in all directions, but those so the structure is for instance like this, right? And we had this is that emitting part, right? And we said that the light actually gets emitted in all directions, but beyond this beyond so if this angle of incidence becomes if it's smaller than critical angle, you have light coming out. But then if this angle of incidence happens to be larger than the critical angle, if this angle becomes greater than theta c, then what will happen is the light gets trapped, right? So that is what is actually giving rise to this Lambertian profile, right? That kind of phenomena is what is giving rise to Lambertian profile. So I hope that answers your question. Michael Jordan has one more question. I understand that relaxation oscillation and also the photon lifetime fixes the maximum frequency bandwidth. Apart from that, does relaxation oscillation has any other effect over modulation light? So that's again a very, very nice question. I'm glad you asked that question. So we talked about the frequency response of the laser, right? This is magnitude of HFF of the laser, the frequency response of the laser. You know that this is, we are talking about direct modulation lasers. Okay, so as you uh, so this is a laser, and you typically forward bias the laser. This is CW condition, but then on top of that you give a sinusoid. So that's when you have so in the Li curve, light intensity versus current, uh, this is the Li curve of the laser, and what you can do is around this bias you can modulate the current, and so you will have once you modulate the current, you will have the output modulated. So this is how direct modulation works. The question is, how fast can I modulate? And we learned about this in the class. We said that the modulation, the fastest frequency is decided by the relaxation oscillation. How does that work? So the at the relaxation oscillation frequency, you have the response which becomes nonlinear. Okay, which means that so you will have something like some uh, let me just call it as some fr, right? So which means that if you try to modulate this at frequencies which are close to fr, what you're going to get is a nonlinear response. The output of the system is, so if you're modulating for instance at this frequency, the output is constant in the sense that you give this frequency to the system, the output is going to give you the same frequency. But if you're trying to modulate at frequencies closer to the relaxation oscillation, the output is nonlinear, which means the system behaves like a nonlinear system. Which what's the consequence of that? You would have modulated with, let's say, f2 for instance, but you will start getting some frequencies, different frequencies, third order harmonics, and so on, right? So you don't want to push your operating frequencies close to the relaxation oscillation. So that's the effect that the relaxation oscillation will cause. So I hope that answers your question. Now, please type in if you have any other questions. In the meantime, let me also look for any forum questions. So there was a question about some confusion of multiple values of B in assignment 4, assignment 5. You can pick any value, and if you can match with any of the values, that is fine. There's a question on can we use a 90-degree phase shifter instead of phase modulator? You can do that. This is probably in an IQ modulator. So in an IQ modulator, we had two child modulators. Which is basically operated at the null, followed by a phase modulator, which does that 90-degree phase shift. So the question is, can I use a 90-degree phase shifter? In fact, you are using a 90-degree phase shifter. This phase modulator is itself acting as a 90-degree phase shifter. You want a variable control, because what happens is because of environmental fluctuations, what you thought as 90-degree phase, if you had given a fixed phase difference, that may keep changing. And what is 90-degree phase is also dependent on the exact frequency of operation, and hence you want it to be something that is variable rather than a fixed 90-degree phase shift. So you want to keep it fixed. I don't see any other questions. So if you do not have any other questions, we can close the session. If you have, please type in. Okay, so one more question from Michael Jordan. Dual polarization phase modulation system. Can the polarization be LCP and RCP instead of SNP? Uh, though the polarization will change due to birefringence. So whether it's linear or circular, the polarization will change due to birefringence. Again, very, very interesting question. All I'm really glad that you're thinking this way, Michael. All what you need is when you say dual polarization, all what you need is orthogonal states of polarization. Now, it could be LCP, RCP. It could be vertical, horizontal. It could be 45 degree, 135 degree, right? It could be left elliptical polarization, right elliptical polarization, and so on, right? It could be any orthogonal states of polarization. The only reason why we choose, and also, by the way, the fiber birefringence can modify all of these, right? It's not just that it can modify only LCP and RCP, it will modify whatever state of polarization you send in, the fiber birefringence is going to modify it. The reason why we are picking horizontal vertical, right, is only because of the ease with which you can generate these polarizations. So for example, how do you generate a horizontal and a vertical polarization? All what you need to do is to pass it through a linear polarizer, or the way it is done is usually in a coherent communication system. You take a laser source, you split into two components with an optical splitter, and then you put a linear polarizer and you put another linear polarizer. So the way to do that is uh, uh, well so you want these to be orthogonal also. So you want this two polarizations to be, if this is horizontal, the other has to be vertical. So what you do is not a simple splitter, you do what is called as a polarization. So one part goes in, another part, one part gets reflected, and then you use probably a mirror, and the other part comes in. Of course, there are no free space elements. I'm just showing here to represent the functionality, and this is your output. Right, so this could be X polarization. These are polarization beam splitters. Now, these polarization beam splitters are devices which are made of double refracting material, such that it splits it into horizontal components and, let's say, vertical component. In a fiberized form, this whole thing will come in single input, two output. One of them will be X polarized, or horizontally polarized. The other one would be vertically polarized. Again, it just means horizontal doesn't mean universal horizontal direction. It just means that the light that's coming out will have orthogonal polarizations, right? Uh, this is very easily done in a polarization beam splitter. Whereas if you were to generate a circular polarization, you would need a linear polarization first, and that has to fall at 45 degree on a quarter wave plate to generate your circular polarization. And if you want to do a left circular polarization, that has to fall on a quarter wave plate at 135 degree. So that alignment, all that becomes very cumbersome, and hence we don't use right and left circular polarization. But in principle, we can, so long as they are orthogonal, we can. It's just that the components that makes the linear polarization is much far more compact and simple than the set of components that will give you the circular polarization. Okay. If there's any other question, please type in. Otherwise, we are good to stop today's session. We will meet again on Tuesday to discuss specifically week 6 and assignment questions in week 6. Try the questions. As I said, I will not give you the answer, but I can tell you if you are getting stuck in concepts, so that you are not answering because you did not really understand the concept. That should not be the case. That's the purpose of having this meeting, contact hour on Tuesdays. I don't see any other questions. Since there is a lag, I'll wait for a couple of more minutes and then log off. Okay, so there are no more questions, so I will log off from the session. Thank you very much and stay safe, everyone. And whichever part of the country you are, happy Durga Puja, Durga Puja, happy Navratri, happy Puja.